Assalamualaikum and a very good morning to Dr. Azudin and fellow viewers. We are from Group 1 and today we'll be presenting about Experiment 6, which is torsion of bar. Okay, for the introduction, the diagram shows that the torque is a measure of the force that can cause an object to rotate about an axis. Just as force is what causes an object to accelerate in linear kinematics, torque is what causes an object to acquire angular acceleration. Torque is a vector quantity, and the direction of the torque vector depends on the direction of the force on the axis. The objective for the experiment is to investigate the relationship between torque T and the angle of twist of a circular cross-section bars and to determine the modulus of rigidity G of materials. Moving on to the next part, which is scopes. So number one is to find the angle of twist by setting the rotation scale at 200 millimeter at the fixed clamp and the pointer was set at 0. And the number two is to record the torque values with different materials of road bars used, which are nylon, steel, and aluminum with different length 200 millimeter and 250 millimeter. And the third one is to calculate the modulus of rigidity by using different weight of load consists of 1, 2, 3, 4, and 5 Newton. The next one is theory. So the theory states that T over J is equal to tau over R is equal to G times theta over L, where T is equal to the torque applied at the end of the shaft, J is equal to polar moment of inertia, tau is equal to the torsional stresses produced in the shaft, R is equal to the radius of the shaft, G is equal to the modulus of rigidity, theta is equal to the angle of twist, and L is equal to the length of the shaft. Carry on with the theory part. So tau is equal to F over A, where tau is equal to torsional stress, F is equal to pressure applied, and A is equal to area. Okay, moving deeply into the next theory, which is for solid rod. So the theory is J is equal to pi over 2 times C to the power of 4. For the hollow rod, J is equal to pi over 2 in brackets of C to the power of 4 minus C I to the power of 4, where J is equal to polar moment of inertia, C is equal to outer radius, and Ci is equal to inner radius.
Experimental setup. So for the first thing we have is fixed clamp, then twist angle scale, rotation clamp, ruler, loads, hanger load, big pulley and small pulley. Then we also using digital caliper, and these three are the material we use, which are nylon, steel, and aluminium. And the last thing is the spanner. So for the next one is methodology. First, the aluminium alloy rod was clamped in position and the load hanger was placed on the cord. Secondly, the rotation scale and the pointer was set at 200 mm at the fixed clamp and the pointer was set at 0. Then, a load of 25 Newton by 5 Newton increments was added and the twist of the rod for each increment was recorded. Fourth, the load was removed and the rotation scale and pointer was set at 250 mm from the fixed clamp. Then step 1 to step 4 was repeated for steel and nylon. Then, for nylon, a load of 5 Newton by 1 Newton increment was added and the twist of the rod for each increment was recorded. Lastly, the diameter of the rods was measured and recorded in the table according to the type of materials using the digital caliper.
Next, we move on into the documentation, data and calculation. For the data and table, we have data table. Data table consists of torsion head effectiveness diameter, torsion head effective radius, and conversion of 1 degree to radian. This is a table 1. Table 1 is a table for the aluminium alloy rod in diameter of 9.34 mm. In this table, we have column of hanger load, twist of rod over 200 mm and over 250 mm in degree. Then we have torque in Newton millimeter and angle of twist rod over 200 mm and over 250 mm in radian. Next, we have table 2. Table 2 is for the nylon rod. Nylon rod diameter is 6.5 millimeter, and the table consists same with the table 1. Also, we have hanger load, twist of the rod in degree over 200 and 250 millimeter, torque, angle of twist rod in radian over 200 millimeter and over 250 millimeter. And the last one, we have table 3. Table 3 are the table for the steel rod in diameter of 4.90 millimeter. In this table, we have hanger load, twist of the rod over 200 millimeter in degree, torque, and twist of the rod over 200 millimeter in radian. This table don't have twist of the rod over 250 millimeter because the data that have we collect is same with the twist of rod over 200 millimeter. So I put just one data here because it's same value. Next, we move on into the calculation part. We have 5 calculation here. First, calculation of polar moment of inertia J equal to pi d over 2 power of 4 over 2. Next, we have slope of the graph M equal to theta over t. Then we have calculation for G and into at 200 equal to L over Jm. And then we have the G for 250 equal to L over Jm also. And lastly, we have percentage of error equal to experimental value minus theoretical value over theoretical value times 100. And for the percentage error, we don't consider negative. Next, we have graph 1. Graph 1 is a graph of the angle of twist rod in radians against torque in nanometer millimeter in Newton millimeter for aluminum alloy rod. In this graph, we can see that angle of twist rod over 200 millimeter is more increasing than the angle of twist rod over 250 millimeter. Next, we have the graph 2. Graph 2 is a graph of the angle of twist rod in radians against torque in Newton millimeter for the nylon rod. In this graph, we can see that angles of twist rod over 200 millimeter have more increasing other than angle twist rod of over 250 millimeter. Then we have graph 3. Graph 3 is a graph of the angle of twist rod against torque for the steel rod. In this graph, we can see that angle of twist rod over 200 millimeter is increasing, and for the 250 millimeter, I don't put it here because the line of the graph is same, so we cannot see the difference of the line. Lastly, we have the percentage of error. Percentage of error for the aluminum alloy rod we have obtained is 11.45%. Percentage of error for the steel rod we obtained 7.81%. Percentage of error for the nylon rod we obtained 19.48%. For the theoretical value, you can refer it in at the reference number that I have put here in the reference slide. Thank you.
Precautions. First, tighten the fixed clamp and rotating clamp to avoid the dropping of loads from the pulley. So for the solution is put a book at the below of the loads to reduce the impulsive force if the loads drop. Then, solution 2 is wear covered shoes to prevent injury. Next one, make sure the rope is aligned with the pulley to avoid error in twist angle reading. Solution, check the position of the rope is aligned before tightening the rope and before conduct the experiment. Lastly, make sure the indicator, which is the cable type, is point at zero of twist angle reading to avoid zero error. Solution: check the position of the indicator before proceeding the experiment. Then the eye must perpendicular to the twist angle scale to avoid parallax error.
So further discussion, from all the graph that is obtained, we can see that when the angle of twist is increased, the torque will also increase. Different material will have different torque. The length will also influence the steepness of of the slope. So we can conclude that the torque is directly proportional to the angle of twist of the material, which are nylon, steel, and aluminum. The percentage error for aluminum, steel, and nylon rod are 11.5%, 7.81%, and 19.48% accordingly. Since the percentage error are less than 20%, we can say that the experiment is a success and we have obtained the objective of this experiment. These are the references that has been used to make this lab report. Thank you.